In this lecture, we are supposed to learn the principles of reliable data transfer. This is related to the TCP protocol, and to understand the TCP protocol, we need to study in advance about the principles of reliable data transfer. Comparing to other chapters, this chapter is not very important in undergraduate course, but this may be a little bit important in the graduate course, but in the undergraduate course, this one may be skipped. I will explain briefly and in past mode, and some redundant slides are omitted. Before going into this subchapter, we look at the concept with the animation briefly in the supplementary website. Okay, let's look at these interactive animations in this supplementary website. This one is helpful for better understanding, thus we learn here in advance. Okay, here in this left menu, interactive animations, you can see this chapter 3, and here 4 animations are here. Among them, we'll learn this one first. Go backend protocol. Let's click this one. Then we can see this go backend protocol. At this moment, you don't need to worry about the details of this go backend protocol. Anyhow, we learn in this chapter later, after learning the general concept about that with this animation. Let's read through this one first. This interactive animation brings to life the go backend protocol. In this demo, the sending window limits, this is the sending window, limits the sender to a maximum of 5 outstanding unacknowledged data packets. This one, 1, 2, 3, 4, 5. That is 5 outstanding unacknowledged data packets. To create new data packets, click Send New. Send New is here. And this action will begin moving data packets between sender and receiver. Let's click this one. Then you can see this one is a packet from the sender to the receiver. And there will be some acknowledgement, this one. And we are learning about this after reading this one. This action will begin moving data packets between sender and receiver. To simulate loss, select the moving data packet or acknowledge, and then press Kill Packet Acknowledge. Okay, I'll show you. I'll send another one, and I'll click this one, and I will kill that one. Then that is lost. Intentionally, we can emulate that loss. That is a kind of error. We are providing this error intentionally to learn about the protocol operation. And this one was the explanation about that. And use pause and resume. Later, another one is automatically it is being sent. That the protocol is doing that. Use pause and resume to make selecting easier. Okay, I'll click this one to send. Then I'll click this one, and you can pause this one or resume. Then you can make it stopped, paused. After that, you can start again with this button, like this, to make selecting easier. And you can select this one, and okay, to select one. Okay, let's try to finish this one. Okay, I'll send again another one. Then here pause, and you can select this one in easy way, like this, because that is post, and you can kill like that. This one is explain about that. Speed up or slow down. Speed up or slow down the simulation by clicking faster or slower button here, and be patient for retransmissions. Okay, I'll show you that retransmission after certain timeout period. Automatically there will be some retransmission, and this protocol is doing that. We are learning about that. Okay, let's start from the beginning. Send new, and I want to select that. Then you can pause this one, and you can select this one, and you can kill like that, and resume. Later, after a certain timeout period, automatically that is being sent. That is called retransmission. You can observe that later. This go back and protocol is working in that way, like this, because that is lost. To proceed to the next normal operation, that should be sent again. That protocol is doing that. Okay, intentionally you can send other packets, that is emulation, and you can pause, and you can choose anyone to kill. Okay, I'll choose this one, and I will kill and resume. Then that second one that was killed, and let's look at what's going on. Even though that is killed, that was acknowledgement. Successfully that packet was arrived here. Only that acknowledgement. Okay, I received that packet very well. That is a kind of acknowledgement. That is lost. Even though that was lost, this one is going to the next step after successful completion of the previous sending. And we can start again like that. And here I'll click pause here because that is moving, and I'll kill. Then let's see what's happening, because that is missing here, and you can see those are successfully received, and those are not received yet, even though those are arrived, and among them this one was missing, and you can see what's happening. And here, be patient for retransmission. See, this is the retransmission, and you can see many packets are sent at the same time, and after that all of them were sent successfully and received successfully here, and we can proceed to the next step for next transmission, because this is one packet among whole complete file. Thus we need to complete to finish that completion of file. Okay, here let's look at this one. Send window size equal 5. Window size means this one. This is the window size. That is buffer size, like storage size. 1, 2, 3, 4, 5 packets can be contained there. Receiver, you can see this one is send window size. That is storage buffer. Only one single packet can be stored there. So small. Window storage buffer. That is main characteristic of go back and protocol. And let's move to the next. After below this, after finishing that sending and receiving and some protocol operation, we can see that description here. This one is describing each transaction. Here, packet 9 received, cumulative acknowledge for packets up to and including 9 cent, packet 9 delivered to application. We learn about these cumulative acknowledgements. This is acknowledgement, but cumulative acknowledgement we learn later. Packet 10 receiver, because there were many transactions, and each one is described here. First, start timer for packet 0. We are using timer, and this one is starting timer, and that is mainly for packet 0. This S means sender, R means receiver, S means this one, and R means this one, receiver. And the sender, packet 0 is sent. Press pause to be able to kill packet. This one is explaining about that action. And the receiver, packet 0 received, cumulative acknowledge for packet up to and including 0 sent, packet 0 delivered to application. In this way, each operation, transaction that is being described here, thus you can understand in easy way. After that, stop timer, start timer, those are all operation of this go back and protocol, and we learn. Okay, I am showing you briefly about this animation. And here we are using some sequence number to differentiate, to identify each packet from others. Base 11 and next sequence number 11, like that. This is the sequence number. To maintain and to send and receive successfully, we are using this kind of sequence number, and that is being used by this go back and protocol with other things we learn anyhow later. You can refer to this go back and protocol animation to understand better about the TCP protocol scheme, and we'll learn from the beginning after finishing this one. This is the sequence number in the sender side. Also, this is the sequence number in the receiver side, and we need to send many packets, and we are trying to check whether that is being sent successfully or not, because this one is providing the guaranteed transmission, because TCP is perfect protocol, and it is providing that the website. And we'll be back. We learn about basic principles of reliable data transfer. As I mentioned already, this reliable data transfer is related to the TCP, Transmission Control Protocol, in this transport layer. UDP is not providing this reliable data transfer service. Thus, this one is mainly for the TCP. Okay, important in application, transport layer and link layers, top 10 list of important networking topics, this reliable data transfer, and this one is application layer. We can see here sending process. This one is sending this data, and that transmitted data will be received by this receiver process, and the intermediate transmission channel, this reliable channel, will be used for that. And in terms of functionality, this application layer is doing the sending process, and in the transport layer, below this layer, among 5 layers, this transport layer is providing this reliable channel. And to implement that service, how to implement? Our main concern is about this transport layer. How to provide this reliable channel, and to provide this reliable channel, we need to design and develop this one. That is our main concern, and the others are explaining about that. Here, reliable data transfer send function, this one is using this data, and this module is about the reliable data transfer protocol sending side. And this one is calling UDT send to send this data packet through this unreliable channel. This one is providing reliable channel, but this one is using unreliable channel. Thus, this one should serve to make reliable channel. And through that unreliable channel, that transmitted data will be arrived there, and this primitive function will receive that, the reliable data transfer receive, and through that reliable data transfer protocol, receiving side, that will be delivered to the application layer. Characteristics of unreliable channel will determine complexity of reliable data transfer protocol. RDT means reliable data transfer. That is the acronym for that. We'll start from this. Let's focus on that. Transport layer. This one is about that. Above is application layer. Below is network layer. That is providing a reliable channel. Here, sending side and the receiving side. Here, RDT send. This one is called from above, for example, by application layer program, and pass the data to deliver to receiver upper layer. And this one is calling UDT send primitive function to transfer packet over unreliable channel to receiver. And in the receiving side, this RDT receive, this one is called when packet arrives on receive side of channel. And after that, this deliver data, that function will be called by RDT to deliver data to upper layer. And reliable data transfer, we are concerning about that, and we want to design and develop that reliable data transfer module. How to? And this one is explaining about that in step-by-step approach. We will incrementally develop sender receiver sides of reliable data transfer protocol, that is called RDT, and consider unidirectional data transfer for simplicity, but control information will flow on both directions. We will use a finite state machine. This is finite state machine. We can think that module is a kind of finite state machine to specify sender side and receiver side module. Here, finite state machine, this one is explaining about that concept. This scheme may be used to design and develop our protocol. And in this finite state machine, the definition of that state means when in this state, next state uniquely determined by next event. We are using these states. The number of states, whole number of states, that is finite. That is called the finite state machine. Using those states, we are designing some machine that is called the finite state machine. Here's some notation. Here above this line, that is about the event. Below this one is action. What kind of event? This event is causing state transition. If that event is happening, then the state is being changed like that. And during the change, some actions will be taken. One state change, transition. Thus, this notation is event, about event, and below this line is about actions. That is a finite state machine notation. Thus, into that scheme, we can design very primitive reliable transfer module over a reliable channel. Because we are trying to understand, thus we are starting from the beginning in step-by-step approach. Underlying channel perfectly reliable, and we are assuming, even though that is not unreliable, even though that is not reliable, we can assume. No bit errors. That means no loss of packets. Ideal case, but in our real world, it is not happening like that. Always there may be some errors, and always there may be some loss of packets. That is real situation in our internet. Separate finite state machines for sender, receiver. Here, this is the finite state machine for sender. We are designing the protocol, thus this one will be used. This finite scheme will be used to design our transport layer protocol in the sender side, also receiver side. Receiver reads data from underlying channel. And this notation, finite state machine notation, this one is state, waiting state for call from above application layer to send some data. This one will be called, and this one is the waiting state. Thus this circle means waiting state. In the receiver side, also this one is waiting for call from below, but from below. And here there is some transition. This one is the event for that transition, but this one is self-looping. Still, it is in the same state. Reliable data transfer send. Data will be sent using this primitive function. And this one is the action. To send packet, the data will be changed to packet. Thus, this one is making packet due to that data, and this data packet that is being used to send through the below layer. And in reverse way, this one is waiting for call from below. Some packet is arrived there, and this one is receiving. And some primitive function is called here, and this one is extracting. This one is the action for that. Extracting packet data and deliver that converted data using this primitive method. And we are using other notation because that is using other version, because the primitive one was using very ideal situation, but this one is considering a little more about the realistic situation. Channel due to bit errors. That means there may be some error because that is real situation in our real world. Underlying channel may flip bits in packet. That means that 1 may be changed to 0, or 0 may be changed to 1, like that. There may be some corruption. That is called error. Thus, we need to use this checksum to detect bit errors. Then the question is how to recover from errors. Think about our analogous example. How do humans recover from errors during conversation? If we couldn't hear well enough, then we can say, pardon me, then the other person will say again. Like that. That is a kind of a general protocol. Here, let's think about this version. Underlying channel may flip bits in packet, as we we read already, and the question is how to recover from errors, and we can use this acknowledgement. Receiver explicitly tells sender that packet received okay. This one is meaning that receiver received the packet well. And also this one is negative acknowledgement. That means receiver couldn't receive that packet, and that was not successful. Receiver explicitly tells sender that packet had errors were lost, then sender should retransmit one receipt of not acknowledgement to solve that error situation, because transporter layer is providing reliable data transfer. If we are using TCP, then that is providing that reliable data transfer. New mechanisms in this version. Error detection scheme is being added, and the feedback, control messages, acknowledgement or not acknowledgement, those are added from the receiver to sender. The protocol is becoming more complicated, more complex, because we are considering more realistic situation. In that case, our real protocol is becoming more complicated and complex. This is the notation. This one is a little bit more complicated. Finite state machine. This is sender side. We are considering other factors. This one is using another state from the receiver side, whether that is being received well or not. Thus, this one is using another state, another waiting state. That is waiting for acknowledgement or not acknowledgement from the receiver side. From the below layer, that will be arrived. Let's look at this one. This one is same. This primitive function will be called from the above application layer, and due to the data, then this one is making packet using that data and send the packet into some checksum like this using the below layers that will be transferred to the receiver side. And this event is okay. This is the transition from this state to this. This is waiting state, waiting for acknowledgement or not acknowledgement from the receiver side. This is waiting state from the application layer to call from above layer to send. And from this state, if that is received packet and that is successful, that means that is acknowledged successfully, and this is the logical operation successfully, and this is simply changing the state and no action. This is called null action. Let's look at this one. Reliable data transfer receive primitive function that is receiving packet, and this one is checking that is not acknowledged. Then send again. UDT send packet using that primitive method. Because there is some error and that was not received successfully by the receiver, this one is sending again. Okay, let's look at this receiver side, finite state machine. Here, this one is waiting state for call from below. If this arrived here, then this reliable data transfer receive function or primitive method, this one is receiving packet, and that is corrupted one, and then this one is sending, that is not acknowledged because that is corrupted, because that is error. And still it is staying in that state. And if that is the successfully received using this event, we can provide this action, receive the packet, and that is not corrupted, and then that received packet is successful one, and we can use that packet and we can make that data and deliver to the upper layer. And also we can send to the sender side that packet was successfully acknowledged, that is successfully received. The finite state machine is working in this way. This is very primitive example, very simplified one for better understanding. But our real protocol is very complicated. Thus we are trying to study from the beginning by step-by-step approach. And this case is no errors, and also this one is explained about that. Wait for call from below. Wait for acknowledge or not acknowledge state. We are using those states here, sender side and receiver side. Okay, if there is some error, some slide may be omitted because we don't need to go into detail about that, and more general concept is enough. Let's look at this one. This version, Reliable Data Transfer 2.0, has a fatal flaw. You don't need to memorize this version number and that detailed finite state machine about that. Just we are learning some concept, how this scheme is being working. What happens if acknowledge or not acknowledge corrupted? Sender doesn't know what happened at receiver and can just retransmit. Possible there may be some duplication. To handle duplication, sender retransmit current packet if acknowledge or not acknowledge that is corrupted. That means there is some error. Then sender adds sequence number to each packet. To solve that duplication, we need to differentiate between the previous one, next one. Thus we need this sequence number. That's the reason why we are using sequence number. In our real TCP protocol, we are using this sequence number. That is the reason. Receiver discards, doesn't deliver up to the application layer, and this duplicate packet. Receiver discards this, throw this away, this duplicate packet, because that one, same one, was received successfully already. Thus this duplicate packet is not needed. Most primitive protocol is stop and wait protocol. Simply sender sends one packet and then waits for receiver response. Send, stop, and wait for that receiver's response, acknowledgement from the receiver. So simple. And this one is explaining a little more about that. Sender is using sequence number that is added, and that is in the packet. We are using that sequence number, and those are called header. Original data and some added header, those are all complete packet to send to the receiver. And simple case is we can use two sequence number 1, 0. But this one is asking that may be sufficient. And actually we are using 32-bit sequence number. This one is not enough. Must check if received acknowledged or not acknowledged corrupted. Twice as many states. State must remember whether expected packet should have sequence number of 0 or 1. And receiver side must check if received packet is duplicate 1 or not. State duplicates whether 0 or 1 is expected packet sequence number. Receiver cannot know if it's less acknowledged or not acknowledged received OK as sender side. There's 0 simple sequence number to 0, 1, that is not sufficient enough. Actually, as I mentioned already, in our TCP, we are using 32-bit sequence number. More advanced one, but still that is not enough. Actually, we are not using not acknowledge. We are using only acknowledge. Thus, this means not acknowledge pre. That means without NAK, without not acknowledgement protocol we are using. Same functionality like our previous one, using acknowledges only. Instead of not acknowledgement, receiver sends acknowledgement for last packet received OK. Receiver must explicitly include sequence number or packet being acknowledged. When that is being acknowledged by the receiver, it is attaching sequence number. Which sequence number until which sequence number that is being received successfully. That is acknowledgement. In our TCP, duplicate acknowledgement as sender results in same action as not acknowledgement. Retransmit current packet. Thus, if there is any duplicate acknowledgement, there is no not acknowledgement. Instead of that, if there is any duplicate acknowledgement in our TCP, I will explain a little more in detail about that protocol later. At sender side, that is retransmitting the current packet again. It is assuming, so sender is assuming if there is any duplicate acknowledgement, then after that packet, that's sequence number, after that sequence number, that is being lost. There's something wrong. And we'll learn a little more in detail about that. That is about TCP protocol. This one is more advanced one. Channels with errors and loss. New assumption. We are considering more realistic situation. Underlying channel can also lose packets. That is more realistic situation. Data or acknowledgement, anyone can be lost. Thus, we are using checksum, sequence number, acknowledgements, and if there is something wrong, then we should send. The sender should retransmit. But still, we should consider something more. Sender wastes reasonable amount of time for acknowledgement. This one is about waiting time. How long? The sender should wait for that acknowledgement from the receiver. If server is waiting, the sender is waiting for a long time, it will take a long time to deliver the lost one or corrupted one. Thus, it will take a long time to proceed to complete of the whole transmission. Retransmit if no acknowledgement received in this time. If packet just delayed and that is actually not lost, and retransmission will be duplicate, but we are using sequence number. With this sequence number, we can differentiate. And the duplicate one will be discarded. Receiver must specify sequence number or packet being acknowledged. Always, receiver is specifying the acknowledged sequence number. That is the way we are learning using our TCP protocol. Thus, we need timer. Let's look at this Finite state machine of this RDT 3.0. Even though this one is not perfect enough, primitive one, this Finite state machine is becoming more complicated. We are using two sequence number here. There's the weight. We are using more states here. Depending upon that, the successful transmission and the wait for acknowledgement 0 or wait for call from above. This one is all about the sender side. And let's look at this one. As we used already in the previous slide, this one is RDT send data from the above application layer. Then this one is making packet and also making checksum, and that will be sent using this UDT send, the primitive method. And after that, it is starting the timer. Because we are using this timer, this one is becoming more complicated because we need to handle that. After that, this one is moving to other state because that is being sent to the receiver, and this one is waiting for that acknowledgement from the receiver. And there may be different sequence number, acknowledgement 0, waiting for that. And then if there is any corruption, this one is checking. Is acknowledged, and this one is corrupted one. And whether that is timeout, this timer is timed out, then this one is sending again that packet because that was lost or corrupted. Thus this one is sender is sending again. And also immediately this one is starting that timer again. And it is moving to other state. And this one is the event. Not corrupt is acknowledged okay, and everything is successful. Then this one is okay. I'll stop the timer, and it is moving to other state. It is going to the next sequence number because we are using 0 and 1 sequence number. Even though we are using 16-bit, this one is just a single bit, 0 and 1. With this single bit sequence number, it is becoming more complicated. But this one is just for simple example to understand better about our real TCP protocol. In this way, it is working. Also, this one is sending data after that. This one is in this state. This one is sending again for other sequence number packet and waiting for that and start timer and waiting for that acknowledgement 1, another segment number, sequence number is 1. In this way, it is becoming more complicated finite state machine. This is mainly about the sender side. Also, there may be receiver side, that even though that is not shown here. Let's move to our other view graph here. That may be better for understanding. RDT 3.0 in action. First, let's look at this no loss case. There's no loss. It is ideal case. Okay, the sender is sending packet 0, and that packet 0 is being sent to the receiver. And receiver received that packet successfully, and this one is sending acknowledgement because that is being received successfully. That acknowledgement that is being arrived there, it is working in that way without any error. And next sequence number, and the sequence number will be 1 and 0 like that. And this one is packet loss case. Okay, here the sender side, this one is sending packet 0, and the first one is received successfully, but next one is in error. During that transmission, that was lost, and that was not received by the receiver successfully. Thus there is no acknowledgement. Thus automatically this timer value will be expired, and that will be time out. And automatically after that interrupt of the timer, after timeout, that same packet will be retransmitted like this, and going to the next normal operation like that. Another case, this one is losing the acknowledgement. Previous example was lost packet, but this one is lost acknowledgement. From the receiver to the sender, that acknowledgement was lost like that. Then still this one is using the timer, and there's no acknowledgement from the receiver. Thus similarly, in the same way, that packet, for packet 1, that timer will be lost. For packet 1, that timer will be expired, and automatically the same packet will be retransmitted like this. Thus here, even though that was successfully received by this receiver, sender retransmitted the same packet here, packet 1. Thus there is duplicate packet here. But still this one is sending that acknowledgement for that duplicate packet here. Another case, sometimes the timer value, if that is not successfully properly set up to the proper value of the timer, then it will be expired in premature time. That is called premature timeout. And it needs more time, but in advance that was timed out. That automatically it will be retransmitted. But actually that acknowledgement will be arrived there after a certain amount of time successfully, but in advance, prematurely, it is retransmitting that. Then in the receiver, this one is receiving duplicate packet, same packet 1 that is received by the receiver. But still this one is the acknowledgement for that packet 1 again here. This one is sending acknowledgement 1, but again here, even though this one is duplicate packet, still this one is sending acknowledgement for that received packet, even though that is a duplicate packet. Okay, let's look at this performance issue of this RDT 3.0. This protocol may be correct, but the main problem is performance. And to understand better about this, let's look at this view graph first, and we'll be back. This one is stop and wait operation, or stop and wait protocol operation. First, sender is sending the packet. First packet be transmitted here, and after a certain amount of time that will be completed in terms of that transmission. That it will take like this time, L over R. That R is the speed, transmission rate, and this one is transported in this way, and this axis means time in the sender side. This is the receiver's time axis, and it is going in this way obliquely because it takes time to be delivered there. First packet that is arrived there, and the last packet bit arrived there, and then this one is receiving successfully. The receiver is sending acknowledgement. That means I received where? That packet. Then after a certain time, that will be arrived there. That means that first packet is successfully arrived by the receiver, and this acknowledgement is explaining about that. The next one will be sent. There's the time here. This is called round trip time. To round trip, and this one is transmission time. If we are adding up this together, and this portion, this is the utilization fraction. There's sender side utilization is like this. This one is meaningful, effective for sending, for transmission. The others are just the empty time, thus not utilized. Thus this one is being utilized. Thus this fraction is the utilization factor. Here we can derive L over R this time, and round trip time this time, plus this one is the whole time delay from here to here. During this time, this one is meaningful transmission time. That is utilizing this communication channel. This fraction is so low because of this stop and wait slow operation. And let's go back to the previous one. RDT 3.0 is correct, but in terms of performance, that is too bad. That means stinks, bad smell. For example, if we are considering 1 gigabps link and 50 millisecond propagation delay time and 8,000 bit, that means 1 kbyte packet size, then the transmission delay will be like this. The transmission time, if we are dividing simply, then that is gigabps means 10 to the power 9. Then that is 8 microsecond. Micro means 10 to the power minus 6. Sender side utilization, that is the fraction of time sender is in busy sending. That means fully utilizing transmission channel. That utilization can be derived as we derived already in the next slide. And here, if we are assuming the real value 30 millisecond for this round trip time, and 1 kbyte packet, that means 8,000 bit packet every 30 millisecond, then if we are dividing this one, 1 kbyte, that is 8,000 bit per every 30 millisecond, then that is 33 kbyte per second. In the PPS, multiplied with 8, around 264 kbps per second unit throughput over 1 gigabps link. Thus utilization is so bad. Why? Because of this bad, not efficient protocol scheme. Network protocol limits use of physical resource, as we observed here. Thus we are using this pipelined protocol instead of the previous stop and wait protocol. Pipelining means sender is sending many packets together. Sender allows multiple in-flight, not yet received, acknowledged, yet to be acknowledged packets. Range of sequence numbers must be increased, and buffering as sender and or receiver. Thus we need some buffer to store there for successful acknowledgement. And here, instead of single packet here, we can send many multiple packets at the same time. We can send like this. Even though those are not acknowledged yet, we can send without, that means add to be acknowledged packets. Later, each packet will be arrived there successfully. Then the corresponding acknowledgement packet will be sent to the sender. This one is stop and wait protocol in operation, very inefficient. And this one is a pipeline protocol operation. This one is efficient. We are using this scheme in our TCP. Two general forms of pipeline protocols, go back N protocol and selective repeat, we are using in our TCP the combination of this scheme. And we learn in detail about this and also about this. In the previous animation, we learned about this a little bit. Also, we'll look at this animation later. If we are using pipelining scheme, then the utilization will be increased like this. Instead of single packet, we are sending multiple packets at the same time like this. Then the utilization will be increased like this 3 times. If we are using this scheme, we are sending 3 packets together continuously, then we can increase the utilization. Here, same explanation about each transmission here, and how long does it take? Same time, and this time is round trip time. We can calculate in same way, but this one is 3 times more than previous example. Thus, we can increase 3 times. We can increase the utilization by a factor of 3 here. If we are sending 4 or 5, then that factor will be increased to 4 or 5. Pipeline protocols, as I mentioned already, in our TCP protocol, we are using this pipeline protocol scheme. There are 2 pipeline protocols. One is go back N, and another one is selective repeat. We'll look at this one first. Later, we'll learn about this later. Go back N. Sender can have up to N acknowledged packets in pipeline. Receiver only sends cumulative acknowledgement and doesn't acknowledge packet if there is a gap. And the sender has timer for all these unacknowledged packet. All these unacknowledged packet. When timer expires, retransmits all unacknowledged packets. Please remind the previous animation in that go back N animation. Many packets are sent at the same time after a certain period of time. That means time out, timer expires. Some packets are sent automatically. That is called retransmission of all unacknowledged packets. And now we'll go back again about this go back again. Also, we'll look at the selective repeat. Okay, let's look at this one first. Sender can have up to N acknowledged packets in pipeline, and receiver sends individual acknowledgement for each packet selectively. And we look at that animation, then we can understand better. Sender maintains timer for each unacknowledged packet. This one is maintaining many timers. This go back N protocol is using only single timer. That's the main difference between them. When timer expires, it retransmits only that specific selected packet, that unacknowledged packet selectively. Thus, this one is called the selective repeat.